So we've been doing derivatives for quite a while, and today we're going to look at what applications the first derivative has when we look at the graphs of functions. So I want you to kind of sketch this. And we're going to say there's a point on the x-axis at M, and then just a point above that. Let's let the y values at N and P be the same. So we're basically going to curve up, stay flat, and then continue on down here. So let's say this is our function. So something you would have learned in the class before this one is how to tell whether a graph is increasing, decreasing, or constant. And you read a graph much like you read a sentence from left to right. And so we would say that the graph is increasing. We're going to use interval notation here from M to N. Okay, so notice this little piece we're increasing. But then notice between N and P we are constant. Constant just means horizontal or flat. And then finally for the last little bit, notice that we're decreasing. We always use parentheses for increasing, decreasing, and constant. Always. Okay, we don't worry about like we do with domain and range, whether we use a bracket or a parentheses, it's just always a parentheses. All right, so this is review. This, however, is not. Okay, if our derivative is positive, okay, in other words, greater than 0. Now, notice that, remember what the derivative is, right? It represents the slope of the tangent. So, in other words, you have a positive slope. So, if that's true for each value in an interval from A to B, then it means the graph must have increased there. That would be the only way that the tangent line would be positive, right? If we were going up from left to right. So notice we're using the derivative to say something about the original function. So as long as we know the derivative is greater than 0, then we know f of x is increasing. Okay, so we're using the derivative to say something about the original graph. So what about when the derivative is negative? So when the derivative is negative, i.e. less than 0, then the graph is going to be decreasing in that interval. So the important information here is if your derivative is less than 0, then the original function must have been decreasing. So notice in the first cases, A and B, we've covered when the derivative was greater than 0, when it was less than 0. What we haven't covered is only if it's exactly 0. Okay? If it's exactly 0, think about what that means, right? That would mean the slope is 0. So if the slope is 0 for a whole interval, then it means that interval must have had a 0 slope or been constant. Okay, so if the derivative is 0, then the original function must have been constant. So all of these things, the summation of that is that the derivative tells us what the graph of the original function f of x is doing. Okay, it tells us whether we are increasing, decreasing, or whether we're constant. All right, so this book may be a little different from other things that you would have learned. If you use the help features on MyMathLab, it's going to use something called a sign chart. So I just kind of want to introduce that real quick. And then I'm going to show you kind of a different variety of it that I use instead. I actually don't use the one that this book likes so much. Okay, but it's fine if you do like it. So let's say that we had a curve that hit at all these spots. So let's say that it curved this way and then that way. Okay, we're going to call this function f of x. So notice it is both increasing and decreasing in certain spots, right? It's never constant. So this is what a sign chart looks like. A sign chart just looks like a number line. And what you place on the number line is any time that you change from increasing to decreasing. So notice we're increasing for a time, right, until we get to x equals -1, and then we start decreasing, okay? So -1 is the significant value. We're going to learn a new name for that here in a little bit, okay? And then we are decreasing until we hit 1, right? So notice what goes on the number line is always the x values, okay? So these are the x values where there's some sort of turning point. Another way to say that is they are x values where the derivative is 0. Anytime we have a turning point, the derivative is 0. Remember, the derivative is the slope of the tangent. Okay, so if you picture my pen being the tangent line, notice right here my pen is flat, right? Also up here my pen is flat. Okay, so that's what that means. So what a sign chart is it uses these turning points and it just asks you to figure out what's happening. Okay, so here we have slopes of 0. And then they just use a series of plus and minuses to indicate increasing or decreasing. So notice here it's increasing. So they just start listing a bunch of plus signs. Okay, they're just trying to say, hey, it's continuing to increase until we hit here. And then notice it starts to decrease. And then at 1 it starts to increase again. Okay, I honestly think that's a little tedious and a little extra, honestly. So this is my version of the sign chart. I don't think it's necessary to list a bunch of negative signs, so I'll go ahead and say 0 and 0 here. And then I'll just do like a big plus. It's increasing here, it's decreasing here, it's increasing here. Okay, so probably from here on out I'm going to do it like this, but the help features on MyMathLab like it like this. Alright, so now that we know what a sign chart looks like, let's talk about, I said we would have a name for what those turning points are. And that name is called critical numbers or values. Alright, so it's any x value in which either of these two things happens. Okay, one is where the derivative is 0. Okay, in other words, where a turning point is, or maybe where the derivative does not exist. So the term we used for that, remember, was differentiable, okay, where it is not differentiable. All right, so let's just take example 1 for a minute. So for example 1 above, the critical numbers are x equals 1 and -1, because those are the points where we had the derivative equal to 0, and or if you want to think of it as the turning points. Okay, it's one and the same. All right, so let's do an easy example, and then we're going to go over some steps for how you always find where a graph is going to increase versus where it's going to decrease. So find the intervals where x squared plus 5x plus 4 is increasing, where it is decreasing, and we're going to use interval notation for this, and where the derivative equals 0. So we're going to find derivative. The derivative of that function is 2x plus 5. And I'd like to know where the derivative is 0. That's one of the things I'm asked to find. So notice if you solve, you're going to get negative 5/2. So that answers part of the question, right? At x equals negative 5/2, f prime of x equals 0. Okay, so I'm going to circle that. That was one of the things I was asked to find. And then I'm also being asked to find how or where the graph is going to increase and decrease. So I'm going to show my version of the number line. Okay, so what I really want to know is it positive or negative? But I know it's 0 here. Let me use a different color because I did that earlier. So we know it's 0 here. The question really is, does it go from positive to negative, or does it go from negative to positive, or is there a change at all? So here's going to be our strategies, and I'm going to lay out this method for you in a bit. We're going to choose test values. Okay, we're going to choose test values, one that is to the left of x equals negative 5/2. Okay, all right, so let's pick something left of negative 5/2. Okay, negative 5/2 is just negative 2.5, so something to the left of that is maybe negative 3. I could pick negative 4, I could pick negative 5. Okay, I just picked the first one that I thought of, which was negative 3. And we're going to test that by plugging it into the derivative. And we're going to see, do we get a positive result versus do we get a negative result? In other words, do I get a positive slope or a negative slope? Notice I get a -1. The number's unimportant. It's just we're concerned with whether we get a positive or a negative. So if I use the version from the book, that means I got a bunch of negatives to the left of negative 5/2. Okay, so now let's pick something to the right of x equals negative 5/2. I have lots of choices. Okay, but anytime I can, I like to pick x equals 0. I mean, you could have picked -2, you could have picked -1, you could have picked any positive number, but 0 is very pleasant to plug in, so that's why I tend to pick 0 when I can. So notice if you plug 0 into the derivative, that should be a plus sign, you're going to get 5. Again, the number's not important. We just care that that slope is positive. So we get positive slopes over here. Okay, by the way, if you tried something other than 0 to the left, or sorry, to the right of negative 5/2, you would find you'd still get a positive. That's why they tend to put more than one plus sign. Okay, and then you just need to figure out what that means. So f of x is decreasing first, right? So f of x is decreasing from negative infinity to negative 5/2. And then f of x is increasing from there on after that. So we're going to say increasing from negative 5/2 to infinity. Okay, so notice that's the second piece that I was asked to find. So these turning points are significant because they indicate that we've had a change of some sort. All right, so the steps for finding intervals of increasing and decreasing. So we're going to do some of varied difficulty, so let's write down some steps so that we remember how to do that. The first step is you need to find the critical numbers. Okay, remember the critical numbers exist anywhere the derivative is 0. But don't forget, we're also concerned with where the derivative just doesn't exist at all, where it is not differentiable. Okay, so if you look at that worksheet that I printed out or that I uploaded this week, that looks like it's got warm up on the top of it, and it asks you where the graph is differentiable versus not. That's what I'm asking you here. All right, step number 2 is you're going to plot the critical numbers on a number line. And I want you to decide if f prime of x is greater than 0 or if f prime of x is less than 0 for each section. Okay, note that each section will be separated by the critical values. Okay, so if the derivative is 0 or if the derivative does not exist, we will split the number line up at those numbers. They are critical. They are in the important numbers where some sort of change happens. And then last but not least, it's really more of an observation. If a section is labeled with a plus sign, it means the graph increases. And if it's labeled with a minus sign, of course, the graph decreases. By the way, kind of a small note, but notice I haven't gotten out the graphing calculator. So I know you could punch these in the graphing calculator. That's not exactly the point. The point is for us to determine some things about the graph without looking at the graph already. Okay, we're going to actually come up with what the graph should be based on this information and some other things we'll talk about in the next lecture. All right, so let's say I told you to find the intervals of increasing and decreasing. And all I give you is x cubed plus 3x squared plus 1 is the function. Okay, we're not going to graph this to try to determine it from that. We are going to just use critical values and see if we can figure it out. So step 1 is to find the derivative, which is 3x squared plus 6x, and set that equal to 0. Factor if necessary. Notice this doesn't require a hard method of factoring. We just look to see what they have in common. So if we pull a 3x out, we'll have x plus 2. So I end up getting x equals 0 here, right? If you set 3x equal to 0, it'll be x equals 0. And I get negative 2 here. Okay. Remember what the name for these are. These are critical numbers. By the way, we don't have to worry about this function being differentiable or being not differentiable anywhere because it's a polynomial. Okay, so we're really just looking for where the derivative is 0. So notice on the number line what happens. You mark the values that are of interest, in other words, the critical values, and we write 0 here. Okay, technically speaking, this is supposed to say f prime of x equals. Okay, so in purple I'm doing what the derivative is doing so that I can tell what the original function is doing. So notice I have 3 sections, right? So I want to pick some test points, and whichever test points I choose, I'm going to plug these into the derivative. I'm going to plug these into the derivative to try to figure out, is it positive or is it negative? Okay, so let's pick 3 test points. So you want to pick 1 to the left, 1 in between, and 1 to the right. So if I pick negative 3 to the left, skip a little space. If I pick negative 1 in the middle, and if I pick 0, not 0, right? I can't pick 0, but I need to pick something to the right of 0, so let's just say 1. Okay? These aren't the values you have to pick. These are the ones that I chose because they're the smallest numbers that fit the category. So now let's plug it in. So f prime of negative 1. So if I were you, I'd go back to this version of it. You can do either this version or this version. But if you do 3 times negative 3 and then negative 3 plus 2, okay, you get 9. And that is positive. So I'm just going to put a big fat positive sign there. Okay. The only part of this that is significant is the fact that it's positive. Don't even really care what the number is. Okay, so now let's plug in negative 1. So 3 times negative 1 and negative 1 plus 2. Okay, so that'll be -3 times 1 or -3. Again, the only significant part of this is the fact that it's negative. So the middle is a negative. And then last but not least, I don't know why I wrote +1 there, but you don't really have to have the +1. But if I do 3 times 1 times 1 plus 2, I get 6, right? And the important part of that is the fact that it is positive. So up here I have a big fat positive. So if I read my sign chart, it tells me where I'm increasing and where I'm decreasing, right? I'm increasing from negative infinity until I hit -2. But I'm also increasing from 0 to infinity. And the only spot where I'm decreasing looks like in between the two, from -2 to 0. So if you're shaky on your interval notation, you're definitely going to need to brush up on that. Okay, this whole section, and the one after it for that matter, uses interval notation. All right, so I'm going to be lazy here. I'm going to say same instructions. In other words, find the intervals where the graph is increasing and the intervals where it is decreasing. All right, so I've got f of x equals 1 over x minus 2. Now, I could do quotient rule on this when I go to find the derivative, or I could rewrite this as x minus 2 to the -1 power. And I can find the derivative using the power rule as long as I remember that technically I'm supposed to do chain rule. So move the power out to the front, reduce the power by 1, and then multiply by the derivative of the inside, but notice that's just 1. So I end up getting -1 over x minus 2 squared. Now I'm supposed to set that equal to 0. Okay, when you have a fraction and you're trying to make it equal to 0, you really are just looking for where the top would be 0. Notice nothing makes that 0. Because the top is a -1, there's no x there. Nothing is going to make this equal 0 because the top can't be 0. Okay, but I do have a problem. I do have something that would make it not differentiable. Okay, but there is an x for which the derivative would not exist. Okay, so even though I can't get the derivative to equal 0, there is an off-limits value for x. Okay, notice that at x equals 2, the derivative does not exist. And of course that's because we can't have 0 in the denominator, right? That breaks our long-known algebra rule. So by definition then, this is a critical value. Remember, critical values are not only where the derivative is 0, but where the derivative is not able to be found. So let me show you the difference when you look at the number line. So we're going to show 2 on the number line. But rather than saying 0, we're going to say that the derivative is ND, and this stands for not defined. Okay, so we're talking about the derivative here in purple. But notice I can still do my test points. Okay, what am I going to do with these test points that I choose? I'm going to again plug these into f prime of x. So notice I only have 2 sections, right? I have something to the right and left of 2. Okay, so I'm going to maybe pick x equals 0, skip a little space. That would be to the left of 2, right? And then if I want to pick something to the right of 2, maybe I could pick x equals 3. So what do I do with these guys? I plug them in, okay, and see what happens. So I plug them into the derivative. So here's the derivative, right? And I see what happens. So if you do -1 over 0 minus 2 parentheses squared, okay, don't lose sight of your signs, right? This would be a -1 over a +4 because -2 times itself is +4. But the only significant part of this is not that it's a fraction. It's the fact that it's negative. So a big fat negative sign goes there. So now let's plug in 3. negative 1 over 3 minus 2 parentheses squared. Notice that's negative 1 over 1, okay, or just negative 1. Notice that is negative as well. Okay, so notice in this case the graph is actually never increasing. It's just decreasing from negative infinity. Now here's where you decide if it's just decreasing all the time. If this is not defined, we have to skip over it. If it were defined, we wouldn't have to skip over it. But 2 is not even a value that's allowed. Okay, if we get 2, we have 0 in the denominator. To review you on something we did for test 1, that means there's an asymptote at 2. Okay, but it means both sections of the graph are actually decreasing. Okay, never increasing. All right, let's do one more, and then we're going to talk about what else the number line can tell us. So, same instructions. But let's say that I give you something that looks like it's going to be ugly. And it is probably uglier than the other ones. So I want to find the derivative. So the first thing is I'm going to rewrite this. So if I go to find the derivative, okay, the derivative of 1 is just 0. So then I just need to do some power rules, right? Move this power out to the front and you get minus x to the negative 2. Move this power out to the front and you get minus 2x to the negative 3. So in other words, you get negative 1 over x squared and you get minus 2 over x cubed. And we want to set that equal to 0. So as algebraically weird as this looks, we're going to factor out what these things have in common. Okay, we can factor out a negative 1 over x squared, and let's talk about that for a minute. If you divide this by itself, you'll just get a 1. And then if you divide this by this, there'll just be a 2 over x left. Think about this. You're dividing out a negative 1 on top. You're dividing out an x squared on bottom. That's essentially all you're doing. And then we'll set that equal to 0. So notice we have negative 1 over x squared equals 0. Okay. Notice that actually can't ever happen, right? For the same reason as the one before it. But I do know that x cannot be 0. Okay, why do I know that? Because that would make this denominator 0, and I'm not allowed to have that. Okay, and then I can also set 1 plus 2 over x equal to 0. So you can algebraically solve this. The easiest thing to think of, though, is what would this number need to be so that it would cancel out with this 1. So we want this whole fraction to be negative 1, because 1 plus negative 1 would be 0. So you can do the algebra there, but you'll end up just getting x equals negative 2. So try that out. If you do 1 plus 2 over negative 2, you get 1 plus negative 1, or 0. Okay, so these are both critical values, but they're critical values for different reasons. And we're going to note that on our number line. Okay, hopefully you see why. So let's show our number line. We have a critical value of negative 2 and 1 at 0. But the difference here is at 0, I have no derivative, or not defined, right? And then here, this is actually a 0. Okay, so two very different reasons, but they're both critical values. So let's pick some test points. So just save yourself some room. So you want something to the left, something in between, something to the right. I think we've already had this similar number line. It just had different, I think we had 2 zeros there instead of a 0 and a not defined, but we can pick the same test points. So let's pick negative 3, negative 1 in between, and maybe 1 on the right. Okay, so go back up to the top and find your derivative. Here it is, okay, and plug it in. So yes, you might have to use your calculator on this. So negative 1 over negative 3 squared minus 2 times negative 3 cubed. Okay, use your calculator and the math fraction key, but you get negative 1 over 27. But again, we don't care specifically what we get. We only care that it's negative. Sorry about that. So this is a big fat negative. Okay, let's do the same thing for negative 1. So negative 1 over negative 1 squared minus 2 over negative 1 cubed. I'm just copying this equation, sticking the number in. So all of that mess actually comes out to be 1. Okay, the significance of the 1 is the fact that it's positive. So we have a positive result in between. And then last but not least, negative 1 over 1 squared minus 2 over 1 cubed. Okay, this becomes basically just negative 1 minus 2, which is a negative 3. By the way, you can shortcut these problems. If you can already tell that it's going to be a positive or a negative, you don't have to write down what the actual result is. You can just note whether it's a positive or a negative sign. All right, so notice now I look at my number line for my answers. So it is decreasing first. So it is decreasing from negative infinity until negative 2. But it is also decreasing from 0 to infinity. And it only increases in between. From negative 2 to 0. Okay, so the last thing that we're going to be able to tell from this same number line is we're going to be able to tell whether or not we have a relative minimum or a relative maximum. Okay, now I think we know probably that a minimum is a low point, but a relative minimum is a low point on a certain interval. Okay, so let's take this graph for instance. Now if I asked you for what we would call the absolute minimum, it doesn't have one because it keeps going down forever. But if I asked you to focus your attention in the middle of the graph and tell me if you see a minimum, then I think we could say that this is one, right? So it's not the overall minimum, but it is a minimum for the middle part of the graph. Okay, so that's what it looks like on the graph. How are we going to be able to tell that just from the equation? Well, first of all, it'll only be at a turning point. Okay, what was the name for turning points? Remember, critical values. So a critical value x equals c will be a relative minimum. I want you to write this down, then we're going to talk about how I don't think you should actually have to memorize this. I think it makes sense. If the graph was decreasing, and then changes to increasing, so it was going down, and then it makes a turn back up, well, at that spot where it made the turn, it would be a low point, right, a minimum. So this is a disclaimer. It's a minimum as long as the function is differentiable there. In other words, if it's not even able to happen at that value, then it can't be a max or a min. So that's why it's important on your number line to put ND for not defined. If you have ND for not defined, then that will never be a value you'll choose for a max or a min. Okay, so let's talk about relative max, and then we're going to look at an example of this. Maybe we'll use an example we've already done today. So I think you can probably guess what the definition is. A relative maximum is a high point on a certain interval. But again, the word relative just means in a certain spot or in a certain section of the graph. So if you draw a curve that looks kind of like the one we did up there, now if I asked you to find the overall max, you would have to say there isn't one, right? Because it goes up forever and ever and ever. Okay, but if I asked you again to just look at the middle portion of the graph, then this could be considered a relative max. Okay, and those will also always exist at critical values. But instead of the graph changing from decreasing to increasing, it'll be the other way around. Okay, so a graph x equals c will be a relative max if the graph was increasing. So picture like a roller coaster going up, right? The graph was increasing and then all of a sudden it starts to decrease, right? Well, where it made a change would be a high point of the graph. And we still have this disclaimer, as long as the function is differentiable there. If it doesn't exist there, then we will be unconcerned with that point as a whole. Okay. So for our final example, let's pull back in a problem we already did today. So I want you to see if you can find the relative max and min for example 3. So rather than us start from scratch, okay, we're going to just use example 3. So let me recreate what we got in example 3. The critical values were at -2 and 0, right? And this is the pattern that we got. We got zeros for these. We had a big plus over here, a minus in the middle, and a plus there. So I'm just copying that from example 3. So notice what this means. Our graph is increasing for a bit, and then once it hits this value, it starts decreasing. So what does that mean would exist right here then? Okay, if we're increasing and we change to decreasing, there's a relative max here. In other words, that's a peak, that's a high point. And then here, we're decreasing for a time, and then all of a sudden we start increasing again. Okay, so that means there's a relative min here. So the only thing that's really left on this one is we have to actually find the full points. We have the x values, now we need the paired y values. So to find the points, because that's what I'll actually need to do, I'm going to need to find the y's. Okay, I've said this a couple times this semester. How do you always find the y's? Well, you just plug the numbers back into the original equation. So look back at example 3, right? But if we do f of -2, it's going to be, the function was x cubed plus 3x squared plus 1. That was the original. So use your calculator and you get 5 there. And now let's do the same for the other critical value, 0. So 0 cubed plus 3 times 0 squared plus 1 equals 1. So we have these pairs here. So the relative max, if you look back at the graph, right, or the number line, is the point -2, 5. And the relative min is the pair 0, 1. All right, so while you're kind of finishing that up, let's look at what the graphing calculator shows us for this. Okay, so I haven't really used that today, but I want to talk about how you can kind of use the calculator to kind of back yourself up. So here's the original function, right? X cubed plus x squared plus 1. Let's graph it. Okay, so notice we have, it's a little hard to see from the graph, to be honest, but notice we have kind of, trying to figure out why my graph doesn't look like I want it to. Oh, because I typed it in wrong. That would be a good idea if I'd actually type it in right. Right, this was example 3. I looked back at it quickly and didn't look at it close enough. All right, that's better. All right, so notice at -2, 5, we have a peak, right? We have a high point, okay, so that's our max. And then notice we have a low point at 0, 1, and that's our min. Okay, so your graphing calculator can certainly back you up. All right, and then one more term. It's really not a new term, but a lot of times they will ask you for the relative extrema. Extrema is just the plural form of the extremes. So when it says extrema, it's talking about both the relative max and min. So don't let that terminology throw you if it asks you for that. It just wants the relative min and the relative max. So let's find the relative extrema for example 5. Okay. So again, I'm going to recreate example 5. So in example 5, we had the same critical values as example 3, but they were a little different, right? We got a 0 here, a not defined here, and then we got this pattern, negative plus negative. So notice we are decreasing, right, for a time, and then we start increasing. So that means that spot must have been a low. So this is my relative min. Okay. Notice the difference here is I am going from increasing to decreasing, but the problem is this 0 is not defined to begin with. So this is not a max. It's actually not a point at all. It can't be a max if it's not first a point. So in this case, there will be no relative max at all. Okay. So in this case, all I really need to do is plug in -2 to the original to find out what the paired y is. So if you look back at example 5, the equation was 1 plus 1 over x plus 1 over x squared, right? So use your calculator. It can be your friend on this. You get 3/4. So there is a relative min at -2, 3/4, and there is no relative max. By the way, let's say that you forgot to indicate on your number line that there was a point that was not defined there. When you went back and tried to plug in 0 to find the y, you would find a problem, right? You wouldn't be able to plug in that 0 anyway. Okay, so in that case, you should be able to tell there's no max no matter what.